Hello everyone, and thank you for taking the time to join today's session. My name is Chin, the sales manager of Hoperf, and today I'm going to walk you through Hoperf's LoRa and sub-1 GHz solutions, along with the broader LPWA low-power wide area technology landscape and some application scenarios of the LoRa and Sub-G product.
CMT23108 to CMT23108 868 MHz outdoor range test settings. Set up the transmitter according to the test requirements. Set up the receiver according to the test requirements. Turn on the receiver, turn on the transmitter, and verify that communication is working normally. Keep the transmitter fixed in one.
And third, we'll dive into Hoperf's product portfolio, including both LoRa and sub-1 GHz FSK modules, and then explore some typical use cases like street lighting and smart metering. So for this session is not just to introduce products, but to give you a clear understanding of how these technologies can help you design better, more efficient IoT systems. So with that, let's get started. Let's begin with the basics. What exactly is LoRa? LoRa stands for long range, and it is a wireless modulation technology based on something called chirp spread spectrum, or CSS. The key idea behind CSS is that it transmits data using signals whose frequency changes over time. These signals are called chirps.
Set FM DEV to 25 kHz and set FM source to X2 AC. Press the mode key and set BERT to on. Set configure trigger to immediate. Set display BER to %. Set total bits to 20,000. Set BER.
Now, why is this useful? Because spreading the signal in this way makes it much more robust. It allows the receiver to detect signals even when they are extremely weak or even buried in noise. And this is exactly what gives LoRa its two most important characteristics: very long communication range and extremely high receiver sensitivity. Now let's compare this with more traditional modulation methods like FSK and also briefly OOK. In FSK, or frequency shift keying, data is represented by switching between discrete frequency points. So each symbol corresponds to a specific fixed frequency. Similarly, in OOK, the signal is even simpler. It's basically turning the carrier on and off to represent data. In both cases, during a single period, the signal stays at a constant frequency, or in the case of OOK, is either present or not. But in LoRa, things work differently. Instead of using fixed frequencies, LoRa encodes data using cyclic time shifts of the chirp signal. In other words, the information is not in the frequency itself, but in where the chirp starts within its cycle. For example, one symbol might use a chirp that starts at the lowest frequency and sweeps all the way up. Another symbol might start somewhere in the middle, sweep to the top, and then wrap around back to the lower frequencies. So even though the waveform looks similar, the timing shift encodes different data. This approach provides a significant advantage. Because the signal is spread over a wide bandwidth and encoded in time rather than just frequency, it becomes much more resistant to interference and noise. Now that we understand the LoRa at the physical layer, let's move one level up and talk about LoRaWAN. LoRaWAN is the network protocol built on top of LoRa. It defines how devices communicate, how data is managed, and how the overall network is structured. It is actually a low-power wide area network standard defined by the LoRa Alliance, using an open MAC protocol to connect battery-powered devices over wide area networks. LoRaWAN is specifically designed for IoT applications. It supports secure bidirectional communication, device mobility, and even localization features, while still enabling relatively fast and flexible deployment. Let's take a look at the network architecture. LoRaWAN uses what we call a star of stars topology. It means that end devices do not communicate directly with each other. Instead, all end devices send their data directly to the gateway. These gateways act as transparent bridges. They forward the data to a central network server, typically through standard IP-based connections like Ethernet or cellular. On the back end, the network server and application server work together. The network server is responsible for managing the network. Things like device authentication, data deduplication, and routing. The application server processes the actual application data and delivers it to end-user systems. The most commonly used platforms include Chirp Stack and the Things Network, also known as TTN. Overall, LoRaWAN achieves a very good balance between long communication range, network capacity, and low power consumption. This is why it has been widely adopted worldwide, especially in applications where devices need to operate for years on battery power. So let's take a look at the LPWA market. Right now, the global LPWA market is growing very rapidly and is increasingly becoming the backbone of large-scale IoT connectivity. As more and more devices need to be connected over long distances with very low power consumption, LPWA technologies are becoming essential. If we look at the numbers in 2025 alone, annual shipments of LPWA devices are expected to reach around 230 million units. And this is not slowing down. The market is expected to continue growing steadily over the next few years. Now, in terms of technology, LPWA can generally be divided into two categories. On one side, we have cellular technologies like NB-IoT and LTE-M, which operate in licensed spectrum. On the other side, we have non-cellular technologies such as LoRa and Sigfox, which use unlicensed spectrum and offer more flexibility. At the moment, NB-IoT and LoRa are the two dominant technologies in this space. But what's interesting is that non-cellular solutions, especially LoRa, are gaining more attention in scenarios where private deployment and flexibility are important. And this is where LoRa really stands out. It has become one of the most important non-cellular LPWA technologies, particularly for private and hybrid IoT networks. By 2025, LoRa device shipments are expected to reach about 95 million units globally. And looking ahead, it's projected to grow at around 15% annually through 2029. In fact, by 2029, LoRa could account for nearly half of the entire LPWA market. So overall, this shows very strong momentum and widespread adoption across different industries. Now, on this slide, we are looking at a comparison of different wireless technologies used in IoT, including LPWA technologies as well as Wi-Fi for short-range communication. Different applications have very different requirements in terms of communication range, power consumption, data rate, and network scalability. So this comparison helps us understand where each technology fits best. LoRa uses CSS modulation or chirp spread spectrum. One of its key advantages is its excellent communication range. In urban environments, it can typically achieve around 2 to 5 kilometers, and in rural environments, it can easily reach 15 kilometers or even more. NB-IoT is based on licensed cellular networks. It provides reliable coverage and strong signal penetration, which is especially useful in applications like smart metering and asset tracking. But at the same time, it involves higher costs and dependency on network operators.
Let's look at some examples. CMT2110A ESR, low cost 240 to 480 MHz OOK transmitter. Version A minus 40 degrees Celsius to plus 85 degrees Celsius SOT23-6 package tape and reel. CMT2119A CMT230A EQR. Ultra low power sub-G transceiver version A minus 40 degrees Celsius to plus 85 degrees Celsius QF. CMT2189D EQR. Sub-G OOK FSK transmitter SOC version D minus 40 degrees Celsius to plus 85 degrees Celsius QFN20 package tape and reel. CMT2
Wi-Fi Hello operates in sub-GHz frequency bands. Compared to traditional Wi-Fi, it offers longer range and lower power consumption, making it more suitable for IoT and smart city applications. Actually, there is no single wireless technology that fits all applications. If we look at LPWA technologies like LoRa and Sigfox, they are specifically optimized for ultra-low power consumption and long-range communication. This makes them ideal for large-scale deployments of battery-powered sensors. Now, let's take a closer look at the key technological advantages of LoRa. First, LoRa provides long-range communication capability. This is mainly achieved through spread spectrum modulation and forward error correction (FEC). Compared with cellular technologies, LoRa can achieve up to twice the communication distance. This extended range significantly reduces the number of required base stations, which helps lower overall infrastructure costs. In addition, LoRa maintains reliable connectivity, even in challenging environments, such as urban areas with obstacles or underground settings. Second, LoRa is based on chirp spread spectrum modulation. In this mechanism, signals are transmitted as frequency-swept chirps, and different spreading factors are orthogonal to each other, which allows multiple transmissions to coexist on the same channel without interference. This greatly improves the spectrum efficiency and network scalability. Third, LoRa is designed for ultra-low power operation. It supports energy-efficient features such as deep sleep mode and automatic wake-up for data transmission. Through system-level optimization, LoRa devices can achieve a battery lifetime of 5 to 10 years on a single charge. This makes LoRa especially suitable for battery-powered devices, such as smart meters, like water and gas meters, as well as agricultural and environmental monitoring sensors. Let's now look at the LoRa ecosystem and its technology roadmap. At the core of the LoRa ecosystem is Semtech, the pioneer and key silicon vendor of LoRa technology. Over time, other companies such as ASR have also joined the ecosystem as licensed silicon vendors, further contributing to its development. Hoperf has been a long-term strategic partner of Semtech and plays an important role in the LoRa module ecosystem. From the roadmap, we can see the evolution of LoRa technology. In 2012, Semtech acquired scalable and released the first-generation LoRa transceiver SX127X. Around the same time, Hoperf was among the first companies to launch LoRa module solutions, such as RFM95W and RFM98W, among which the RFM95W has become a classic product and is still widely used today.
Then there's the CMT2392F512EQR transceiver SoC. Its RF core has the same performance and specs as the CMT. A quick note on the SPI interfaces. The CMT2300A uses a non-standard 3-wire SPI. The 3 wires are CSB chip select, SCL serial clock, and SDA bidirectional serial data. The CMT23108, on the other hand, uses a standard 4-wire SPI, CSB chip select, SCLK, serial clock, SDI, serial data in, and SDO, serial data out, for both registers and FIM.
In the same year, Semtech also introduced the third generation LoRa&Sub-1G series supporting sub-G 2.4 GHz dual band and even S-band satellite communication, and Hoperf launched the RFM92LRW module based on LR1121. In 2025, Semtech released the fourth generation LoRa transceiver with multi-PHY support and high-throughput FLRC capability, and Hoperf will release the RFM93 LRW module based on LR2021 soon. As a strategic partner of Semtech and ASR, Hoperf continues to align closely with the latest technology trends and market demands, providing high-performance LoRa module solutions for a wide range of IoT applications. Here, we introduce our LoRa module portfolio. We provide a wide range of modules that cover different application requirements, including different frequency bands, output power levels, and package types.
In terms of selectivity, it has an adjacent channel rejection of 30 dB and a blocking figure of 70 dB at 1 MHz offset. That's not top tier, but it's perfectly adequate for its cost-effective positioning. When transmitting at 13 dBm, it typically draws 23 mA. At the max 20, in receive current is about 8.5 mA, and sleep current is just 300 nanoampere, which is 0.3 microampere. This is aimed at applications like wireless metering, smart homes, industrial remote controls, security systems, and wireless sensor networks.
In addition, the RFM92LRW supports sub-GHz LoRa, 2.4 GHz LoRa, and even S-band satellite communication, providing advanced flexibility for emerging use cases. Overall, the goal of our module portfolio is to give customers maximum design flexibility while significantly reducing development complexity. By using pre-certified modules, developers can shorten their design cycle, lower certification effort, and reduce overall project risk. Now, let's highlight one of our latest products, the RFM92LRW module. This module is based on Semtech's LR1121 chip, and what makes it stand out is its multi-band capability. It supports sub-GHz LoRa, 2.4 GHz LoRa, and even S-band communication, enabling much more flexible system design for developers. The module's dimension is 23 by 17.5 mm and features two RF ports separately designed for sub-GHz and 2.4 GHz operation. With its advanced multi-band support, the RFM92LRW can be widely used in applications such as smart metering, building security systems, and smart city infrastructure, providing a powerful connectivity solution for next-generation IoT deployments. Next, we move to LoRaWAN modules. In fact, the LoRa transceiver modules introduced earlier can also support the LoRaWAN protocol when working together with a host MCU. However, to further simplify system design, we also offer LoRaWAN modules based on SoC solutions, where the MCU and RF components are integrated into a single chip. This integration brings clear advantages, including simpler hardware design, fewer external components, and faster development cycles. In addition, this module RFM6601W comes with FCC, CE, and KC certifications, which can significantly simplify the certification process for end products and help customers accelerate their time to market. The RFM6601W and RFM6601 SEW modules are based on an ARM-based SoC solution, offering a high level of integration and performance. These modules support a maximum transmit power of up to plus 22 dBm and provide up to 256 KB of flash memory and 64 KB of SRAM, enabling sufficient resources for a wide range of IoT applications. In addition, all modules come with factory-programmed firmware that supports LoRaWAN class A, B, and C, allowing for flexible deployment in different network scenarios. Designed for easy integration and reliable performance, these modules are particularly well suited for applications such as smart metering, street lighting, and asset tracking. Now, let's shift to another important technology, FSK. FSK remains widely used in sub-1 GHz communication due to its simplicity, robustness, and cost-effectiveness. Globally, leading companies such as TI Silicon Labs and Semtech provide FSK solutions. At the same time, Hoperf also has a strong presence in this market, offering a wide range of FSK and OK-based products. Each year, we ship more than 300 million RF chipsets, with around 30% of them being FSK-based products. In addition, we have served over 3,000 customers worldwide, including many well-known global companies. Our products deliver performance comparable to other leading suppliers while offering excellent cost effectiveness, which has been increasingly recognized by our customers. Our sub-1 GHz module portfolio includes multiple product categories to meet different application needs. It covers Silicon Labs-based modules such as those built on SF4, 463, EFR32 FG23, and EFR32 MG25, as well as RF69-based modules. In addition, we offer our CMT series modules, including products like RFM300W, RFM310W, and RFM380F64W. This diverse portfolio provides customers with the flexibility to choose the most suitable solution based on their specific performance, integration, and cost requirements. The RFM310HW module is a high-performance solution designed for sub-GHz communication. It is based on the CMT2310AW chipset, which provides strong anti-interference capability, making it well-suited for operation in complex and noisy environments. In addition, it supports fast and stable automatic frequency control, enabling quick frequency hopping for enhanced communication reliability. Certain versions of the module, like RFM310HTW with TCXO, also support ultra-narrowband operation with bandwidth as low as 1.3 kHz. With its excellent reliability and robust performance, the RFM310HW is ideal for industrial applications such as automatic meter reading, home security, and building automation. Another two modules we would like to highlight are the RFM25A12W and the HMWS001. The RFM25A12W is based on a high-performance sub-GHz SoC from Silicon Labs, featuring 1,152 KB of flash and 256 KB of RAM. It supports multiple modulation, including FSK, OQPSK, and OFDM, making it suitable for applications such as Wi-SUN 1.1. The second option is the HMWS001 module, another solution provided by Hoperf for Wi-SUN networks. This module offers a highly convenient approach as it comes with built-in firmware that supports Wi-SUN 1.0. The host MCU can easily control the module via AT commands to create and manage the Wi-SUN network, significantly simplifying system development and integration. We provide a full set of technical resources, including datasheets, reference designs, and development tools. These resources help customers accelerate development and reduce risk. Both LoRa and sub-1 GHz FSK are widely used in many applications: smart cities, industrial monitoring, agriculture, and more. Both LoRa and sub-1 GHz FSK technologies are widely used across a variety of applications, including smart cities, industrial monitoring, and agriculture. Let's briefly look at some typical use cases. In street lighting systems, there is a need to control multiple street lights simultaneously, and in many cases to group and adjust lighting based on different environmental conditions. Traditional solutions rely on centralized switching, which lacks flexibility and cannot achieve efficient energy savings. By using LPWA technologies such as LoRa or sub-1 GHz RF each street light, or groups of lights can be controlled individually, enabling smarter and more energy-efficient operation. Another example is parking management, where it is necessary to monitor the status of each parking space in real time and enable accurate billing. And this also allows drivers to better understand parking availability and make more efficient decisions. In the field of environmental sensing, LPWA technologies can be used to continuously monitor environmental conditions and provide early warnings for natural disasters in remote areas where cellular network coverage is unavailable. LoRa and sub-1 GHz FSK become ideal communication solutions. Similarly, in smart farming applications, these technologies enable real-time monitoring of livestock health and location, helping farmers efficiently manage animal distribution and improve overall productivity. Street lighting is a typical application scenario for LPWA technologies. Key design considerations include robust connectivity to ensure that each street light can be controlled reliably. At the same time, new street lights may be installed at any time, so the network must be easy to maintain and scale. In case of a single node failure, the overall network operation should not be affected. It is also preferable to adopt standardized protocols allowing streetlights from different manufacturers to follow a unified standard. In addition, security is another important factor that must be taken into account. For this application, the recommended solutions include LoRaWAN and Wi-SUN. For LoRaWAN deployments, the RFM6601W module is a suitable choice. For Wi-SUN networks, the HMWS001 module is recommended as it comes with ready-to-use firmware. Alternatively, for customers who prefer to develop their own firmware, the RFM25A12W module provides a flexible solution. Smart metering, including electricity meters, water meters, heat meters, and gas meters, is another key application scenario for LP1 technologies. One of the most important considerations in this field is interoperability, ensuring that all smart meters follow a unified standard, such as LoRaWAN or the widely used WMBRS technology in Europe. For these applications, recommended solutions include the RFM6601W LoRaWAN module for standardized and scalable network deployment. Alternatively, for sub-1 GHz FSK-based solutions, modules based on the CMT2310AW chipset, such as the RFM310HW, are strong candidates. In addition, SoC solutions like the CMT2391F128 and CMT2392F512 also provide flexible and efficient options for smart metering system design. Wireless M-Bus or WM-Bus is a low-power wireless communication standard mainly used for remote meter reading applications such as electricity, gas, water, and heat meters. It is part of the European standard EN 13757 defined by the European Committee for Standardization and is designed to enable efficient, long-range, and battery-friendly data transmission. Widely adopted across Europe for smart metering, WM-Bus typically operates in sub-1 GHz frequency bands and uses FSK modulation, making it a reliable and cost-effective solution for large-scale metering deployments.
Okay, let's start by looking at the hardware for our demonstration kit. As you can see on this slide, the demo hardware has two main parts, the RF modules on the left side. At the top is the CMT2310A evaluation module, CMT2310AEM, and at the bottom is the CMT230A evaluation module, CMT23. When you get this demo kit, you just plug either the CMT2310AEM or CMT2300AEM into the corresponding 10-pin header on the motherboard, power it up, and you're ready to go. The motherboard itself can also be used as a development board. Its main microcontroller is the HC3.
Typically, the WM-Bus tech runs on a host MCU, which controls the radio transceiver. Therefore, it is relatively straightforward to migrate from other transceiver solutions to the CMT2310A platform. In addition, the CMT239F128, with its rich integrated peripherals, serves as a strong alternative to SoCs such as the CC13XX or EFR32FG2X series. Overall, customers can smoothly migrate to Hoperf platforms like CMT2301A and CMT2391F128. And we also provide comprehensive tools and technical support to simplify the migration process and accelerate development. Okay, to summarize today's session, we introduced LoRa and FSK technologies, explored the LPWA market, and reviewed Hoperf's product portfolio and key application scenarios. As a leading manufacturer of IoT key components, Hoperf provides complete IoT solutions, including RF chipsets and modules, LoRa and LoRaWAN solutions, BLE and MITR solutions, as well as sensors and digital isolators, helping customers accelerate product development and bring their solutions to market faster. Thank you very much for attending today's training. If you have any questions, please feel free to contact us at any time. Thank you.